So the next property that we're going to talk about with functions is called continuity. And what continuity means is it's either is a function continuous or is a function not continuous. So most of the time, to tell if a function is continuous or not, let's just take a look at the graph. So I'm going to start just by sketching a random graph here. Here's my function. And so the question is this function continuous? Okay, and really what continuous means is when we're looking at the graph, can we trace the graph without having to pick up our pencil? So really just in one fellow swoop, can we cover the entire graph? So here we go, just trace the whole graph. So yes, this is a continuous function, right? I can trace from beginning to the end without having to lift up my pencil. So yes. All right, so let's take a look at another function. Here I've actually graphed a sketch of the function h of x equals 1 over x. This is known as the reciprocal function. We'll get into that in section 1.3, so pretty soon in the year. But the question is this function here continuous? Well, let's do exactly what I just said. Let's try to trace it. Okay, we trace it. As we get to this point, obviously we're going to have to lift up our pencil and jump to up here. Okay, so no, this function is not continuous, right? I couldn't just trace it without lifting up my pencil. And this is known as an infinite discontinuity, and we'll talk about that in a couple minutes. All right, so talking about the different types of discontinuities, there's 3 types of discontinuities. The first one is known as a removable discontinuity. So in the removable discontinuity, if we look at this graph here, okay, this graph looks like it's continuous, right? I can trace all the way from beginning to end without having to lift up my pencil. However, right here we have this open circle, okay? We have this open circle at the point 2, 2, right? I just kind of put in little tick marks, right? 1, 2, 1, 2. So we have this open circle that is known as a removable discontinuity, okay? Because every other point on the graph we can trace right over. However, at just 2, 2, there's a hole in the graph. And we'll talk a little bit more about, well, where does this hole come from? When would that ever happen? We'll do that in the next portion of this video. All right, so when we talk about removable discontinuities and when would that ever really appear, well, here's an example. This function v of t, okay, and again, same exact thing as f of x. It's just now instead of my independent variable being x, my independent variable is t. Okay, I just want you guys to get used to seeing different types of functions, not always just f of x. So v of t equals t squared minus 2t over t minus 2. So now if I go over and I take a look at that graph, okay, switch to Desmos here, and I take a look at the graph, it looks like just the graph of f of x equals x, right? Just that straight line, right? A linear function that goes straight through the point 0. And what I'm going to tell you is in this graph, there is a hole at the point 2, 2. If we take a look back at the function, if we go back to this function and I try to figure out, well, what's my domain of this function? If I look at the domain, well, I know I can't have a negative underneath a square root, and I can't divide by 0. So I know that t minus 2 cannot be equal to 0. T cannot be equal to 2. So my domain does not include t equal to 2, right? 2 is not in my domain. Well, going back to the graph, it looks like we do have a point 2, 2. However, there actually is a very small removable discontinuity at that point 2, 2. So that's just an example of, well, when would a removable discontinuity actually occur? Okay, the second type of discontinuity that we're going to talk about is known as the jump discontinuity. Okay, with the jump discontinuity, it's exactly what it sounds like. When I try to trace the graph, I can start by tracing over, But then I need to make this jump, right? I'm jumping from this point all the way up to here, and then my graph continues. Okay, so this right here, I made this jump. You could think of that as that being the jump. That's what makes it a jump discontinuity. Okay, and jump discontinuities are going to occur with piecewise functions, which we'll get into a little bit later on in the year. All right, and the last type of discontinuity that we're going to look at is known as the infinite discontinuity. With the infinite discontinuity, here when we try to trace the graph, we're tracing, okay, obviously we have to pick up our pencil right here to get up here. And so this can be confused with a jump discontinuity, right? Because we're making the jump from all the way down here, right? All the way to up here. However, this is not a jump discontinuity because this jump, well, what's the distance of that jump? Here, my arrow is pointing all the way down to negative infinity. Here, this arrow is pointing all the way up to positive infinity. So the distance of that jump is infinite, right? That's an infinite distance with the jump. So that's why it's known as an infinite discontinuity. Okay, and when are we going to see those? Well, this is actually the graph of the reciprocal function, right? The same function that we were talking about earlier. So we can say this is g of x equals 1 over x, okay? And we have an infinite discontinuity at the point x equals 0.